This screen should be pretty representative of, who I am and what I do. I'm an instrument development person, so what I do is I focus on the design and utilization of cameras and detectors and the optics associated with it that can capture, whether it be images or spectra, which we'll talk about a lot today, of the surfaces of planetary bodies. And so I'm going to walk you through spacecraft mission and instrument development in general. I'll stand back here. Why not? This is a telescope back here I'm going to try not to run into. So, what is planetary science? That's one of the big things that I want to be able to answer for you guys today because it's a commonly misconceived industry. For obvious reasons, it's actually one of the newest ones. And I'm going to be talking about how we harness the electromagnetic spectrum for planetary exploration. So I want to first clarify something about NASA that a lot of people either don't understand or haven't looked into or maybe haven't really cared to for obvious reasons because it's a complex bureaucratic government thing, which nobody really likes anyways. But NASA is an umbrella organization. And this is what allows for the planning of some very long term endeavors, as well as funding despite profitability, right? In the private sector, we're always paying for something because we're hoping that it'll get us closer towards something that'll make money. But what NASA's doing a lot of the time is working towards these decadal goals, these decade long goals. And they're trying to do that through a variety of things, including supporting outreach and education in order to make sure that the seed of our future generation is set in stone. And so when I say umbrella organization, I don't really mean this. What I really mean is this, where you have these, large directorates instead of things like a director and a deputy. And then under that, you have these larger organizations, whether that be academia, journals, conferences, etc. What it really ends up looking like is this. So, nothing's really that simple, especially with our federal government. But I'm going to try to break it down a little bit. So this changed recently, I believe in 2021. And now the Exploration Systems Development, or ESDMD, you're going to see a lot of acronyms. So this was called HEOMED. It's basically human operations. So it's the people that are planning things like the Moon to Mars program, or Artemis. And then there's the Space Operations Sector, or Directorate. And they focus on making sure that we have a continuous presence in space, for example, throughout programs like the ISS. The aeronautics program focuses on things like advanced aeronautics, so aircraft. Supersonic commercial flights, one of those things that a lot of people hear about. So we're trying to elongate the sonic boom because the biggest problem with commercial flight is not that we can't get planes that fast. It's that when they go that fast, they're very loud, and we don't need everybody's houses falling apart because there's a sonic boom every 13 minutes. So the solution is to design planes aerodynamically in a way that elongates that sonic boom, and that pressure regime reduces overall the sound kind of effect on the overall population. And this is something that NASA is kind of pioneering on. And then there's a division called Space Technology, STMD, that focuses on essentially the advanced R&D side of space exploration and what NASA does overall. So the image there is of LightSail, which was a program that I think launched 2 missions in total, 2 CubeSats that were designed to test the idea of a light propelled spacecraft. So solar energy has pressure, solar pressure or force, and that's what that was designed to take advantage of. The program that I work under is the Science Mission Directorate. So that's, as it implies, all of the very, very cool science, the missions, the instruments that do those missions, the operations of those missions, and then the analysis of the data that comes from it. And this spans as an umbrella across the nonprofit, private, government, academic, and international sectors. So when we kind of zoom out of this, it generally ends up looking like this, and I'm there at the bottom in this tiny organization at Stony Brook University and called the Center for Planetary Exploration. But I've had the pleasure of being sort of across all of these different, sectors of NASA. When I started early off, it was because of the first robotics program, which, if you're familiar with, is K through 12 robotics program that provides students with the opportunity to, essentially solve real world problems in STEM, like they would in sports. And I went to Purdue University for my undergraduate degree, and I studied mechanical engineering, aerospace engineering, and planetary sciences. When I got into undergrad, I started to get more involved in the field. I started in the defense industry actually, and I'll probably just skip through this because I think a lot of this is in there. A lot of these slides are reused, uh, which I think I wrote a preface for, but I don't know where that went. But I spent a decade exploring 8 solar system bodies from TRL 1 through 9, so TRL being technology readiness level. Um, Intern to PI, so from the bottom to the top with academic, private, nonprofit, and the government sector. So I spent 9 years studying planetary services through spacecraft and rovers, 8 years creating and facilitating curriculum, as well as mentoring in FIRST robotics, writing 6 years of peer-reviewed publications, and 2 years working with the Navy and the MDA. So I started in the defense industry, working on the SM-3, and I was kind of, it was cool. Obviously, missiles, knocking down missiles in space is pretty freaking awesome. But the reality of it was is that I couldn't talk about what I did. I couldn't work with international partners. There was very little collaboration, so on and so forth. So there were a lot of reasons why when I had the opportunity to switch to the space exploration sector, that's what I did. But the point is that I'm pretty privileged, right? These are not universal opportunities. I'm spoiled, as they say, and so I'm going to try to prove that you don't have to be spoiled like me. You can be born anywhere. I was born 5 minutes from the lab that ran the New Horizons mission, the shirt that I'm wearing, the first to go to Pluto. So what I'll say is that this lecture is not comprehensive. I've made this in the last 2 days by like just smorgasbording all of the other lectures that I have from previous times. And I have a big thing happening with my company coming up, and so I've kind of just cobbled this together for you. But when you're on the cutting edge of science, it's kind of impossible to remember or know everything, especially every new data set, inference, and conclusion that you can come up with. So the idea is that space exploration moves very quickly, especially with the introduction of new missions, right? You launch a spacecraft, it reaches a planet, and you wait 10 years to get there, right? And suddenly, oh my God, the pictures come. And, for the sake of New Horizons, right, that lasted a matter of a minute max, right? So you wait over a decade for something that'll happen in 1 minute, and you pray that it'll work, right? So there's boom and bust cycles, but generally there's been a lot more boom because the tech has become cheap. So space exploration is becoming a lot more accessible. And it's important that in industries like ours, in the academic field especially in general, that we use our tools efficiently, our resources, and our references. And that's key because you can never know everything. You can never remember everything. You can never be as quick as a computer, as an LLM, as a neural network, which we're even using in spectroscopy now. So the point is that you need to be aware of where to find those resources and how quickly to use them, and then how to judge them wisely. And this is something that I think you guys have, being people that are on the internet, are well aware of. But I just want to reiterate that this is super important in the field because schools are really still pushing down your throats things like syntax and coding. And in reality, you should be learning about how to plan your code broadly more than you should be learning about how to type every line. So there's a lot of things about what our generation has to deal with that I think are important to consider. And I do want you guys to realize that all of the NASA related work that I might be talking about today is 100% public knowledge. It's up for discussion. It's free for you to access. All of the data is available online, etc. So a lot of people see organizations like NASA as mildly inaccessible, but it's absolutely far from the case. And I consider it to be the only U.S. government organization that exists that is pretty much open to what they want to be able to share with the world, right? They're pretty much open with everything. And the reality of it is that they have to be, because that's the only way to do science, right? You have to be able to work from everybody's ideas, take in all the considerations. And you can't do that for defense for obvious reasons, right? But when it comes to something like space exploration, it's inevitably a human endeavor. So I think that's one of the wonderful things about it that made me fall in love with it. There's simply too much to cover, obviously, for an industry like mine. Planetary science, by the nature of it, includes a lot of the world, right? So there's so many different components of it that I'm not going to be touching on, but just be curious if you're in the audience here. Then, ask questions in the lecture stage. Excuse me. I'm about to burp, is what I was going to say. But ask questions, and that'll kind of get me on tangents, and that's the way I function better. I have a lot of these curated slides that were meant for all these different purposes that I've smashed together, but if you just ask a basic question like, what's the moon made of? It might put me on a rant. For example, if you guys see in the top corner here, I'll actually just go ahead and swap Discord over there. I'm still learning to manage my setup here, but if I enable that, and then so that's a piece of the moon that we have here on the table. Speaking of, and so part of my goal is to try to make this kind of science and this kind of curiosity more accessible, and help people realize that you can buy a piece of the moon, stick it on your desk, and look at it and play with it if you want. Because why not? And I will focus on demonstrating these palpable kind of applications of our science and our instrumentation, right? So this is just a sub $300 microscope. I bought it used, and I bought I think it was like a $4 piece of the moon, right? So if you wanted to do spectroscopy on that, well, you could buy a $200 Raman, spectrometer, which I have in the cabinet there, and you could do that at home. So this kind of science is accessible, and the data sets and resources are there for you. And I intend to, be an accessible resource for that connection to an industry that feels very inaccessible by the nature of it being space. um, so I'm in the middle of building this lab, so yeah, pardon the mess. But I hope to come back sometime if they'll allow me to kind of show you guys some of this instrumentation more than just this microscope. Once we have this built out, all of these shelves are going to be kind of moved out of this room and changed up over the coming weeks. We're even going to be getting an XRD, an X-ray diffractometer, and installing that. So we have a lot of moving pieces over the coming 6 months to 1 year that are kind of because of this. I want a TLDR bias and give you a conflict of interest warning. So I own a company now, and we're focused on the monetization of what would you consider to be unique educational methods. And we fund institutions, and we consider them to be self-sustaining educational and laboratory institutions that kind of facilitate the kind of passion-driven and resource-anchored education that we believe needs to happen as a result of things like LLMs now. And that's what this lab is. It's one of those facilities. It's specific to planetary spectroscopy. But shameless plug along with that bias warning, we're building up these labs, and we intend on funding student projects. So the first round of proposals are going to be coming up in the next year. We're going to fund things between $100 and $1,500. And we just want to give students the opportunity to pursue the projects that ignite their passions in the same way that somebody could buy a microscope at a piece of the moon and be really excited about it, right? But this requires a lot of money in order to make broad, and we intend to get that from private academic and government partnerships and grants. The people that have a stake in the future of our of our species, who are in fact the students, whether they're adults or just graduated high school. So let's talk about planetary science now. What is planetary science? What is it not? Well, it's definitely not astronomy. And this is something that even I kind of struggle with sometimes. Astronomy is observing usually much further objects, right, than what we would be studying, which are in the solar system or terrestrial bodies or planets. So planetary science, right? You can consider astrophysicists or astronomers to be the people that would use the infrared to look very, very far out into space, like with James Webb Space Telescope or something like that, or Neil deGrasse Tyson, right? We're obviously not astrology, but what planetary science is, it's a very broad, multidisciplinary field. So it includes geology, geophysics, geodynamics, atmospheres, hydrology, astrobiology being biology in space. Pretty cool. Aliens, essentially. Volcanology, and that's the cool thing is, you can study aliens and it'd be a legitimate profession. Volcanology, materials science, materials, planetary materials, geochemistry, glaciology, exoplanets, mineralogy. I mean, the list goes on. It's every part of a planet, right? It's quite a big list. But what I do is I study surface processes of terrestrial bodies, so moons, Mars, asteroids, so on. Anything involving formation and change mechanisms of planetary surfaces. Um, I also focus on spacecraft mission development, so the conceptualization to flight, which is TRL 1 through 9, so that's that technology readiness level, so when the technology is ready. And I've worked on programs from 1 to 9, and conceptualization is probably my favorite phase because it's easy to just think about missions from the top level. Oh, I'm going to send this size spacecraft to this body for this reason to do this science. But when you get down into the nitty gritty, being able to interact with engineers, aerospace people, launch vehicle people, comms people, One of the favorite memories I have from the mission development side of my career is going to the Team XC study at JPL. So this is a study where they take your mission design, and we had a CubeSat mission to go to Phobos and Deimos, which are the moons of Mars, and it was a CubeSat mission. So a CubeSat is essentially a satellite that's about this big, and they tear your mission apart all the way down to its bones, right? And then they build it back up. They have one expert from every industry, one comms, one power, one science, one this, one that. And they're all just standing around a room. They give you 3 days to complete redesign it. And it's just very cool to have such an interdisciplinary problem that's at such the cutting edge. And I really enjoyed that about the spacecraft mission development side of things. In addition to having originally an engineering background, I liked being able to leverage those skills. And that also goes along with instrument development. So this is going into what we use on those spacecraft in order to do the science. So this is remote sensors, spectrometers, imaging spectrometers, things like that. And I also have a focus on education modernization. So this is, I'm not going to talk about this today, but it's something that you can reach out to me if you're interested in it. So this is a lot of time what people think planetary science is, and while it is true, I don't intend to do this. I don't know if you can hear it because of the audio changes, but that's, commonly what you would think of. Now, this is what I think of. This is the double asteroid redirect mission. So, in case you aren't aware, there is a guy out there whose job it is planetary defense. So, planetary defense is the field of studying dangerous asteroids and ways to deflect them. And we did a mission called the Double Asteroid Redeflect, where we attempted to change the position of this asteroid, Didymos. It's a two-body system, as you can see, and it was successful. So we essentially launched a kinetic impactor, a big fat spacecraft, into the surface of this small asteroid with the purpose of trying to just nudge its trajectory just a wee bit. Because if we can prove that we can nudge its trajectory just enough, just far enough ahead in time, then as that orbit, projects, it obviously becomes a much great distance, a distance enough to prevent it from hitting the planet. So this is something that we have to think about for the very long term in our field, right? We think all the way out to the heat death of the universe, right? So we're considering how can we protect the human species with this kind of technology. And other examples of planetary science. So a few million years ago, this rock right here fell through Mars's thick atmosphere, plummeted through, and smacked the ground with an energy equivalent to 10 nuclear blasts. That's impact cratering. That's also a field of planetary science. In fact, the person who wrote the original equations on impact cratering, who, by the way, was pretty heavily involved in, the boom side of science back then, he was also the guy who wrote the first equations that dictated, how rocks flowed and moved in, these scales of energy. And it's fascinating if you look up hydrocode simulations. Essentially, entire planetary crusts move like liquid when, these impacts are happening. And the physics of that is insanely hard to model. But later on, we're trolling along. The human species has made this robot called the Curiosity rover or the Perseverance rover, right? And we see this rock, we zoom in and we take a scan of it using LIBS, laser-induced breakdown spectroscopy, and based on the chemical composition and the, basically the look of it that we can figure out, this is a meteorite. Oh, this is actually a iron-nickel meteorite, and these are really unique because these are actually the primordial core of a planetesimal. So a planetesimal is the baby of a planet, right? So as accretion happens and a planet forms, and material glops up in order to form, a terrestrial body, right? You start with just a mix of rock and metal and other things, but eventually you get big enough that you become differentiated, which means just like a lava lamp, the density of liquid, right? Oil and water, remember that experiment as a kid? So the density goes, the higher density stuff goes to the center. That's differentiation, and that's this. So this is the core of a baby planet sitting on the surface of Mars that we found with one of our goddamn robots. And this is 140 million miles away. How is that not freaking awesome? Right? So, what's really fascinating about this industry is the ability to learn the most from the smallest amount of information. Right? This is just a laser dot, right? Just a little prick of light that we're analyzing with such sensitivity that we can determine not only where this rock is from, how old it is, but we're doing all of that from the comfort of our squishy desk with a cup of coffee in hand, you know? So that's the beauty of planetary science. And not only that, but we do that on Titan, right? With the Huygens probe, or Venus. And this is not even us. This is the Soviet era. So a lot of people don't know that the Soviets sent like over 20, I think, landers to Venus, which is crazy for that time frame, right? And the pictures are insane. And there's this crazy story that I always like to tell people. I might have to stand for this one. Where, let me grab, actually, yeah, this is a good example. So this is the camera that is taking this picture here, right? So you put a cover on. But when you actually want to use it, that cover needs to come off somehow. Well, you can't really stick it there, because then as you're flying down, it'll just be flapping around and it'll run into something important and break your spacecraft. So you have to jettison it. You have to get rid of this lens cap, right? And back then, these scientists had to think about some way to, as this spacecraft is falling down to the surface of Venus and about to release its parachute. Because Venus is a thick atmosphere, so you can use a parachute. It pops off the lens cap, and they have to do a calculation. A very stupid, but very reasonable, and you'll see why, calculation of how much it'll cost to prevent this lens cap from falling in such a place that it either prevents this from landing correctly, or it comes back and it hits the spacecraft and damages it. And that risk assessment determines that, well, the risk of this is so low that we're not going to design something in this spacecraft to prevent this from happening. Instead, and this is kind of just a Soviet engineering thing, we're going to send 20 of these, and one of them ought to work, right? Now, NASA tends to just build the most expensive, most reliable thing for the most amount of money because they don't want to look bad, and that's because government funding and all that other stuff. But one of these missions, that lens cap popped off, spacecraft comes down, lens cap lands, and these things had a little spectrometer. It was this arm that would drop down, hit the soil. Soil, by the way, on the surface of another planet, is called regolith. So it would go into the regolith, excuse me. It would measure basic material properties about that regolith, because, for the time that this was. And they get one of the data sets back for one of these missions, and the spectra looks flat, like flat in a way that it shouldn't. And they're thinking, they're scratching their heads, like, what could be wrong? Is the spectrometer broken? And they look at the image. Excuse me, allergy season, sorry. And it turns out that the spectrometer has fallen directly onto the lens cap, which the spacecraft landed near. So you have to plan for these things no matter how unlikely they are. You release that lens cap 100 miles in the sky and still you landed next to it because, god damn it, if it will happen, Murphy's Law, right? So this is Rosetta Philae. This is a beautiful view. I can't get over how just crazy these kinds of images are. It's a video, and to clarify, how much wind is there on Venus? That's an interesting question. I don't know how to really quantify that, but for perspective, I can show you. And it's funny that you ask about Venus, because Venus, I'm relatively new to Venus, actually. Excuse me. Let me pull this up for you. Oh, are you going to be able to see this on my side, or am I going to have to... Here, let me see if I can just share my screen. Oh, you can see it. Oh, well, now I closed it. My bad, guys. There we go. So on Mars, for example, there's a very thin atmosphere, but we still get things like dust devils, right? So we still get these video sequences of dust devils going across the surface. For the sake of Venus, I'm very new, but because it's such a higher density atmosphere, you can expect it to be very significant. What I can do is I can look up a quantification of it would be. So we're actually sending some missions to Venus finally. It's been a long time. Veritas and Da Vinci have recently been proposed, and there's some talk about making sure that this stuff happens. And I have a friend who's doing research in this. But what you can think of, this is going to be kind of hard to explain without going through the rest of the talk. But if you look at it in a particular wavelength, then you can see through the atmosphere, and you can pretty clearly see the atmospheric dynamics. The reason that Venus is so significant, I don't know if you know this, but if you look in the night sky, the brightest point is almost always, if it's a planet, Venus. Now you have to look for the ecliptic, which is essentially where the sun rises and sets. So you look for that line, and along that line, the brightest dot is almost guaranteed to be Venus if it's in view, because it's so thick of an atmosphere that it's just reflecting light, right, over and over and over again. So if you look here, it'll show blue and near infrared light being reflected up here, infrared light being reflected here. There's this cloud region, and you can see it quite literally says sulfuric acid clouds. So quite a not very pleasant place to be. And this will show the average wind speed, which I believe, actually, I think I remember seeing this somewhere. I like to at least provide some references. Caloza and Landis, yeah. So upwards of about 90 meters per second in wind speeds, and the 65, 70 kilometer altitude areas. So we're talking about kind of like Jupiter in a way, where the layer of the atmosphere dictates the speed very, very dramatically, because these atmospheres are made of gases that we don't want to breathe, let alone comprehend, let alone breathe, I should say. So hopefully that helps a little bit. But I'll show you some pretty cool stuff. I mean, this is Jupiter, and who knew Jupiter was so freaking pretty? I mean, whoa! From a distance, it just looks like a literal gas giant, right? But I mean, when you look at it and you stretch its color bands in the right way, you start to see a lot of this variability in its atmosphere that make it so unique. A lot of people don't realize that we actually don't orbit the sun. We orbit around a point that is shared by Jupiter and the sun. Jupiter is such a big planet that the majority of the solar system orbits around it and the sun. And not only that, but I think a lot of people would agree, at least in my industry, in the field of astrobiology, that one of the main reasons that we have life here is that we have this habitable zone, right? This zone where liquid water can exist easily. And as a result of what we believe to be a very bizarre and unique circumstance of having such a large planet form very close to the sun in this solar system. It's very uncommon to have such a large planet so close to the sun. And it wasn't there at the beginning of the solar system. It actually moved, it migrated. And this relates to something called late heavy bombardment. I don't want to get into all that right now, but the point is Jupiter is actually like kind of responsible for everything in the end. The sun's cool and all, it gives us power and energy and blah, 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 photosynthesis, powerhouse of the cell, whatever. The point is that Jupiter is fucking awesome. This is Europa. Europa, my goodness. I mean, I don't know if you guys have heard about icy bodies, but icy bodies are these Jupiter's my goat. Exactly, my man. So icy bodies are fascinating because they're essentially a snowball with a ice shell and a subsurface ocean. And I'm glad that I have this screen set up that I can do this, because it's so much easier to just like Google shit and know that it's a reputable source. So Europa subsurface, and you can see those lines all across it. are actually because of what we believe to be surface features formed by the crust being flexed and moved. Uh, and this is kind of what that looks like, that disrupted ice. I thought they would have a cutaway in this image. Overview, is that it? But we are actually sending a mission called Europa Clipper. This is going to be a little bit much, but I'm going to do it. Europa Clipper is going to be exploring Europa, um, and I has actually had the privilege of working on the Europa imaging system, so ICE, which is the narrow angle camera, NAC, and the WAC, wide angle camera. And you can see we believe that there's a metallic core, so it's differentiated, as we said earlier. There's a rocky interior, and if you zoom in, if I can, there we go. So if you zoom in, you can see that there's this surface, and we have warmer ice, colder ice, and then we have an ocean underneath. And there's this plume process that's resulting in these surface processes. Venus is a great example of the dude. Fango, it's 100% a great point, dude. Yes, Venus is, we call it the runaway greenhouse effect, right? So it's a great example of that. Venus used to look a lot like Earth. We believe also, obviously, Mars, and it has a lot to do with its position and its orbit and its obliquity, but when it comes down to it, it's the same exact problem of what we have here on Earth with climate change. So one thing to consider about Europa and other icy bodies that I think is really fascinating is that this isn't ice like the stuff that you get from your fridge, but this is, or freezer, excuse me. This is like high pressure ice and like CO2 ice. And high pressure ice is just bizarre. The way it works, we really don't understand super well. Now, you can see if we look at this in the full screen, and just keep in mind, I didn't prepare this ahead of time. I just Googled this, and NASA just has this there, so I'm going to use it. That's how awesome the resources, this kind of stuff are. Let's hail Bob. So Jupiter has a bunch of these moons, and what's really cool, and this is the Juno spacecraft, conveniently enough, so that's where that image that I showed you is from. They orbit in a resonance. And a resonance for orbits is where, let's say you have, these are our three planets, and these are orbiting, all right, that's not going to work. These are orbiting around, right? And if I'm in the center, if these two planets have some kind of eccentricity, meaning their orbit has an oval to it, then whenever they're closer to the planet in the center, they're going to be pulling on it. Their gravity's going to be pulling on it a little bit, right? So if, I don't know, how can I do this? This is my planet in the center, right? And we're orbiting like this, then every time these two moons get close to Jupiter, right? We're close to this body, they're getting pulled at the largest possible force, right? And so a resonance is when multiple of these bodies line up in a way that they pull on each other. And this is so significant too, that it heats the interior of these moons. And that's why we have Io, which is this absolutely terrifying volcano of a moon. It is literally just, so there we go, the most volcanically active world in the solar system. Quite so. So what I think it would be important for you to think, excuse me, think about how you can have right here what we call an icy moon, and right here a volcano world. And those are moons, not even planets. And this is planetary science. So, I mean, I'm on slide like 5, so let's go on. Oh, well, I didn't finish this slide, but I did want to show you guys. So CAIs and pre-solar grains. So pre-solar grain, let's see if I can find a picture of it. Right? Minecraft. Where are you at? Calcium-rich inclusion. Somebody up there was asking, did you learn all this in school or is it work experience? It's work experience. Yeah, it's work experience. I had a privilege of going to Purdue, which had an undergrad program in planetary science and a lot of really, really talented professors. And, our industry is growing, so there are undergrad programs around the world. But you don't get this in high school, obviously. You get this from going and seeking it out. And that's something that I think, has made me fascinated with education, is the idea that we can kind of encourage students to find and seek those resources out. But anyway, so CAIs are these, how far into the future are you able to accurately predict orbits? Are you thinking about three-body problem lately? I was talking about this with my chat recently. So not well. Yeah. So it is. So three-body problems are a real thing. When I was at Purdue, we had a professor who was like one of the specialists in them. And so we have these things called keyholes, for those of you that aren't aware of what we're talking about. And if you were to try to take, for example, Bennu actually is a great example. I actually have the statistics off the mind. So essentially, 2036, I believe, is the year. 2182. So sorry. In 2182, Bennu is going to make a closest approach. In Bennu, you'll actually see pieces of Bennu in a little bit. I have pictures here. Excuse me. As we brought pieces of Bennu to Earth recently. That keyhole idea is, let's say, again, we have an orbit. This is us, and this is Bennu. So Bennu, every time it makes an approach, it's coming a little bit closer, right? And imagine like a window here, and little units, little boxes in that window. And each time it goes through, it's going to go through one of these windows. Those keyholes are windows of probability, all right? The reason that they exist is because of something I mentioned earlier, solar pressure. So one of the biggest challenges is not just the three-body problem. It's not just the orbital dynamics of such a complex inner solar system and a rubble pile asteroid, and I'll show you why rubble pile asteroids are so annoying for orbital dynamicists. Essentially, when you have the sun beaming down on one side, so I have a key light up here, and it's kind of visible from that angle, right? So there's a lot of reflection here, right? That's actually producing a solar pressure. And on an asteroid, you can think of it as its energy being applied to the surface, and then volatile components, so gases and things, are being sputtered off or being heated off of that asteroid. And because of Newton's laws, an equal and opposite reaction actually occurs. That's that solar pressure as well. So the YORP, that's a term for it. It's essentially an unknown that we have because it's way too complex of a problem to model when it comes to things that look like this. I'll show you Ryugu, which we have pieces of at my lab at school. So, it's not just a ball. I mean, this looks like a top. So, and there's even more complex bodies, right? So New Horizons target was that's not all right. Well, we're getting that's not what I wanted. But anyway, so see, the point is that there are a lot of uncertainties, and Bennu, for example, in 2182, the likelihood of it hitting Earth, the likelihood of one of these keyholes resulting in it coming back the next time and hitting Earth is the same likelihood as you were to die when you're eating a hot dog. So think about that, I guess, and maybe worry about the glizzies. So the point is that in addition to the orbital dynamics, there's a lot of surface processes happening that people like me have to think about when we're doing missions like the double asteroid redirect or things like that. If I were to tell you how far out we need to know about a hazardous near-Earth object in order to deflect it, at this point, I don't think we could even tap that thing. But maybe if we heard about it within 20 years, a decade would be pushing it. We could successfully deflect it. The likelihood that we would know with enough certainty that we could convince the governments of the world to put the money and the time required to do a mission like that in 10 to 20 years at this stage in our technological process, very low. So give it another 50 years, and I think we will have substantial infrastructure, as we do now for ballistic missiles, for the deflection of asteroids. And if you would like, because this seems like a topic you guys are interested in. We just talked about this with my Twitch chat, because we have a lot of like friends from the Russian community, and this happened in 2011 or 2013. It was 2013. I'm gonna turn this down in case it blasts, but there was a massive fireball that happened in Russia that was captured on. If you don't know, Russia has dash cams everywhere. It's, I don't know what it is with their insurance companies, but they got dash cams everywhere. And this fireball knocked out windows for miles. I mean, it was a significant event, all over the news. You see blowing out doors and things. I mean, it's not unheard of. I mean, nobody's been beamed in the forehead by a micrometeorite, gang style, but it's very likely that sometime in the near future there'll be another fireball event like this that isn't executing people but is eliminating entire cities. So we have to really think about what we do to prepare not only the engineering side of this, but also what I think is really important is the science of it. Because what I'll show you here, we don't understand these big space rocks, right? We did not know what the asteroid Bennu would feel like when we tagged it or touched it in order to sample from it. I'll show you a video of that happening, actually. So let me get to that. CAIs are basically tiny parts of chondritic meteorites, a certain kind of meteorite, that are from the first 10 million years of the solar system. So they're the earliest materials of the solar system. And you can also get pre-solar grains, which are quite literally, as they imply, pre-solar. So they have isotopic signatures that are not of this solar system. So speaking of Bennu, this is Bennu right here, and this is the OSIRIS-REx tag event. It's coming up and bouncing right there. You can see it pop away. All right, that's what it looks like from the top side orbit. But this is a video from the event itself, and you can see it's wildly violent. It's an arm coming down, and then you can see a gas cylinder uses a puff of air to, push the regolith down and up into the cavity to then collect it. And we were hoping to get a bit over 2 ounces. We were hoping that it was a successful collection, and what we believed was a bit over 2 ounces was successfully brought back to Earth. And this was done in 2020. So this is what that looked like, what we believed it would look like before it happened. Okay, so we touch the surface. It's a rock. We stop on it. We do our thing, and then we go away. It's called tag, touch, and go. This is what it actually looked like. And what we realize is that rubble pile asteroids are, as they imply, piles of rubble. They're like ball pits, but very sharp and bad for the lungs. They are more akin to a ball pit than they are a rock. And what we ended up doing was actually dramatically changing the surface of the asteroid. Entire parking lots worth of regolith were shifted by the tag event, by just this one little puff of air in order to suck up this regolith. And it's so understanding how something like this interacts with the surface of a body like the Earth at these speeds, the speeds of it's not easy. So we sucked up that regolith, we stored it away like this, right? And you can see this exact capsule, well, you see those little bits right there? We actually, do I have a picture of this? I don't know if I do. No, I don't. I have to show you guys. Oh, I didn't mean to do that. Hopefully it doesn't crash. But look at this. So we were actually leaking sample. That's not going to be a fun source. Oops. Excuse me. All the way back to Earth. This is what that looked like. I want to see if I can find the GIF of it too. GIF? I forget the... Don't judge me. All right. Nah, I'm not going to click that. There we go. We were leaking regolith. It was just spewing out. all the way home. What's going on? So we end up with a very large amount of material, more than we were expecting, more than actually we were designed to handle. And you can see this imprint that we left on the surface here. This is that gift that I was showing you guys of us actually collecting from the surface. And this has to be one of my favorite kind of examples of, engineering and planetary science aligning. You'll see here that we actually dumped off that sample box, and Osiris Rex is going on to study again. It's going into another body. So these missions are designed to last so long that they can do something like that and then go and continue to another moon or another asteroid or another planet and do another kind of study. So this lands in Utah. We have a high velocity parachute here that's used to get it down to the surface, and then we went and picked it up. And these samples, this is what that looked like. It's a really exciting day. This is quite recently in 2024. We were able to open it up, and what's significant about this is what you're about to see here. We're opening it up in a pristine environment, and the reason is because when something like this, so this is a piece of the moon, a impactor, a rock from space, God knows what it was. It might have been a planet itself at some point, ran into the surface of the moon and fractured off a piece of it. And that piece floated around the inner solar system for God knows how long, until one day it happened to align with the orbit of Earth. And then it slowly got into the point of the atmosphere where it could start to break up and fall down, and eventually it got so close that it eventually just exploded into a bunch of tiny pieces, landed on the ground, and then some guy in Arizona went and picked it up, put it on eBay, and now I own it. That's freaking awesome. And that doesn't even happen with just the moon. That happens with Mars. And that's how I have a piece of Mars over here as well, right? So these are rocks from the surface of another body that have been sent to us by impacts. This is not that. And that's what's key, is these, when they fall through the atmosphere, they get a fusion crust, a crust around the surface as a result of that heating. And these do not, because this was collected from the surface of the asteroid and kept pristine all the way home. And it will be kept pristine till the end of time. And the cool thing about what NASA does with sample curation, is we did this with Apollo, is we lock away a majority of it. Because we know that our instruments are going to get better, right? We know eventually we're going to know more about the moon to have more questions that can be answered with better instruments. And so we lock it away in a place that keeps it not hydrated, so it's not touching the air of the Earth, right? We keep it cold in some cases, cryogenically cold, so it's at the same conditions that it was on the moon. And we do this for the asteroid samples as well. So we've collected samples from Ryugu, we've collected samples now from Bennu, and you'll see these are absolutely stunning images. So this is the actual head that you saw touch the surface in that video and collect those samples. This is sitting in the Johnson Space Center. And this right here is that pesky rock, that little pebble, was holding this TAG-SAM head open. And that's what was causing the leak all the way home. So we figured out the culprit. And I think they called it like the bad actor, the bad one or something like that. But this regolith, and also these are Velcro pads essentially. They're like metal Velcro. That's how we use that to grab some stuff. And then sometimes that was an Apollo thing, wasn't it? Yeah, I think somebody told me that once. I gotta look into that. That's an interesting one. I mean, some of this stuff, you'll notice it's very dark, other than some of these kind of bright patches. And what we found from looking at Bennu from orbit, and you'll see this if I show you some of my research, is that it's actually quite heterogeneous. So homogeneous means it's kind of the same color all around, the same texture, so on. Heterogeneous being that it's got that bit of sparkle on the surface of it. And you know, you can tell that that sparkle has some. I should probably turn this on for you guys over there, shouldn't I? Yeah, let me just change my camera. I totally forgot to do this for you guys. Like 20 people over here who have no idea what I'm talking about. Sorry, guys. Um, and just you look up close, and a lot of these are pretty angular, right? They're pretty sharp looking, and then some of them are more kind of boulderish. They're more, you know, nodulistic, right? Very, very dusty as well. And this is mostly antigrite, which is essentially asbestos. So it's when you look at it at the very small scale, it looks very sharp. So now let's talk a little bit about spectroscopy. So I'm standing on this mountain looking out into nothingness, right? And what do you see? Well, we're looking in the visible part of the spectrum, right? So across the electromagnetic spectrum, across this entire range, you're only seeing 0.0035% of the light. That's 0.0035% of what the entire universe is offering you. And that's like watching me in this video through 70 pixels in total, right? And that's not a lot of information, relatively speaking. And the electromagnetic spectrum can be broken down into these broader bands here. The radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays. I'm sure you guys have heard a lot of these. I won't go into it too much because this is more of an advanced crowd than I think what this was prepared for originally. But what's going on in these parts of the spectrum that essentially you're not privy to? Well, what I do, I forgot to prepare some of these things, so bear with me as I talk through it, is my focus is looking into the visible and near infrared and thermal infrared. So the thermal infrared is this part of the spectrum, right? The longer side. It's vibrational motions of molecules, and I'll show you what that means in a little bit. Emissivity, so actually a lot of this I'll show you. I'm going to kind of skip through a little bit. And then on the other side of it is the visible to near infrared. So this is the visible part, and this is the near infrared part, right? So that's 0.4 to 3 micron. And this is involving electron transitions and vibrational motions. And I actually I think I have some innovations that show that. As well as, you know, you'll see these two things here, linear and nonlinear mixing. So in the thermal infrared, you can determine mineral abundances from, you know, basically extrapolating back from the linear mixing. And in the visible to near infrared, it's nonlinear. So it's a lot harder to determine what the abundance mixture is. And then I won't go into particle size effects here. But if you break this down to the instruments that are being used, now this includes laboratory or orbital. So the one on that corner, right over on this side, I don't know if you can see my mouse. I think you can. That's CRISM, the Compact Reconnaissance Imaging Spectrometer for Mars. So this is a visible to near infrared spectrometer, push broom style detector, and it is studying the surface of Mars. I think you could say from like here-ish to here-ish. This is obviously no scale, but this is on the Mars Reconnaissance Orbiter. And then this right here is actually an instrument that we have in our lab called PARSEC, the Planetary Asteroid Regolith Spectroscopy Environment Chamber, PRSCC, yeah. And this is designed to simulate the surfaces of airless bodies like the moon and asteroids. And we have an FTIR that's actually, this is an FTIR back here, but this is a much nicer one that we have at the university. Excuse me. And what we do is I take samples that are modal mineralogical models, so they are as few minerals as we need to look as close as we can to the surface of Bennu, as similar as we can to the surface of Bennu, and study how dust affects the thermal infrared spectra of these materials at the exact environmental conditions that we see when we're looking at it from orbit. So we have this data from the thermal emission spectrometer on the OSIRIS-REx mission, and this was actually something I started doing before we got these samples back. So it's going to be really cool to kind of take what I was trying to study about these samples from orbit and constrain it using now what we have in the lab once these start to get released to researchers. And I also want to mention that this is so annoying, but the units in this field of work, especially spectroscopy, are aggravating. We have wave number and wavelength and frequency and energy and these all these different things. You kind of just have to deal with it and decide which you're going to speak in for each part of the spectrum. But generally, it's chosen to try to keep the numbers as clean as possible. And so you might hear me mention microns or wave numbers or nanometers. Just bear with me. It's you can kind of ignore the numbers and just know what part of the spectrum we're in, and I'll remind you. Um, but when you hear FM radio, right, that's this part of the spectrum. AM here, and when I was a kid, this was something that was cool to hear because I never knew that. Right, the thing I see in the radio in the car was related to the fundamental physics of the light and how it interacts with matter in the universe. I mean, it's kind of mind blowing. So speaking of spectroscopy, let's get into this a little bit. So when you look at a spectrum like this, I mean, it really this is just squiggly lines, right? What does all this mean? So on, oh goodness, so on the vertical axis, what you're seeing is essentially either the intensity of the energy or the response that it has to that energy. That's because it could be reflectance, it could be absorption, it could be emission, but the point is that it's the intensity. The x-axis there is the wave number, the wavelength, the frequency, or the spectral band. So in the electromagnetic spectrum that you saw, that big line, right? So this right here, this is less frequency and less energy. This is increasing wavelength, so longer length between these two parts. And this is more frequency, more energy, and increasing wavelength. So if we look at these two sides, they actually mirror these two instruments that I have up here, one being CRISM, the visible to near infrared, and this being the thermal infrared. This is oh, I have it backwards, oopsies. This is a thermal infrared spectrum, right here, and this is a visible to near infrared spectrum, let me clarify. And you'll notice that on one side there's reflectance, and this should actually show emission. But they do kind of just look like squiggly lines, don't they? What are we learning from this? Well, remote sensing or spectroscopy in general depends on our ability to take advantage of how radiation or light interacts with matter. And we talked about the different parts of the spectrum, right? And each part of the spectrum interacts with matter in a different way. It changes with the wavelength, the environmental conditions, the sample that we're observing, the instrument we're using to observe, so on. Ooh. So remote sensing depends on being able to take advantage of how radiation or light interacts with matter. You can have stretching, you can have bending, and this is all for the thermal infrared, and this is kind of what I was talking about earlier. This is what that looks like. We can have symmetrical stretching, asymmetrical stretching. I mean, this is getting into some complexities that even I don't really look into too much unless I'm doing the modeling for it. But my advisor and the professor that made this slide, Tim Glodge, this is something that he's really interested in. But we also have similar complex mechanisms happening for the sake of optical spectroscopy, right? We have vibration, stretching, bending, rotation, reflectance, transmission, absorption, luminescence, emission, fluorescence, scattering. I mean, all these different kinds of mechanisms of light interacting with matter, and that's dictating, essentially dictating how these lines look when we look at the spectrum and we look at the surface of a planet. And so I wanted to play, for once, Khan Academy actually had something pretty decent. So this is showing what different parts of the spectrum do to the matter when they interact with it. I'll skip through, and it's a pretty cool little simulation of microwave energy causing a rotation in the molecule every once in a while, infrared rotation causing a vibration in the molecule, right? And then the visible part of the spectrum resulting in, I believe, the rotations and the bending is what he shows, but sometimes passing through. And then he also talks about, he's showing excitation. So you can excite parts of the molecule, you can bring it up to new electron states in the ultraviolet. So it's all about how radiation interacts with matter. And that's what's important to know about spectroscopy and remote sensing in general. So we're using that in our instruments, right? So we're sitting on the surface of Mars. This is a rover, the Curiosity rover, I believe, is what this model is based on. And this is actually an image from one of my early papers. We were walking through these pictures from MSL, and this is taken with the Molly Hands Lens Imager. So it is essentially the equivalent to I have a GoPro there. It's the equivalent to like your smartphone camera. It's the very close up. Okay, I'm walking around. Oh, I'm gonna take a picture of that. Oh, I'm gonna take a picture of that. Right. Whereas the one that's on the top is more of a surveying camera. It's looking over the whole landscape and planning trajectories and tracks and stuff. And I was a undergraduate intern or undergraduate researcher, just clicking through thousands of these pictures of rocks all over Mars, and I came across these like worms, these little wormy looking things. And our research actually found that in this particular region of Mars, the Vera Rubin Ridge, the water, which was all over the surface of Mars at the time, was walking. Water was flowing through the rock and pulling iron out of it. And that iron was reaccreting in these really bizarre kinds of formations, right? And the shape of these formations was dependent on a lot of things, but sometimes they crystallized in these remnants of other minerals, which are called pseudomorphs. So they would have these really bizarre shapes to them. But let's say we have a rover looking at this, little rock, and we actually found that it was metallic in nature by doing what I'm about to talk about. So we have light going to it, and we're using a laser to, send that light over, for example. And it's either going to reflect off of that surface, it's going to hit it and then scatter, it's going to be absorbed by the surface and then re-emit it. So like we were talking about earlier with the runaway greenhouse effect, that's what this is. And then transmit through it. So those are the different possible alternatives for example, optical microscopy, or excuse me, optical spectroscopy. And, this is a draft slide, but this is, me just throwing images on it. But these are actually pictures of the sites that we were looking at for the research that I was doing that I just mentioned earlier with Parsec. We were looking at how dust affects spectra, so these are some of those examples. This is where my slides might get a little bit drafty in nature, so excuse me if there's a little bit of weirdness happening and me trying to explain what I'm looking at, because I've kind of just pasted a lot of these in. In fact, I might just go to this view so I can. Oh no, we're at this part. I'll stick to it. So let's look at this from the perspective of a spacecraft. We're at an orbital region of interest, so we're a spacecraft looking at the surface from the top. And we see these pixels, A and B, A being the bright ones and B being the dark ones, right? For an imaging spectrometer, each one of those pixels is one of these spectra, one of these squiggly lines, right? And so CRISM, that compact reconnaissance imaging spectrometer for Mars, that's what that is every pixel will be another spectra. And if you bear with me, I have 200 slides here, but I wanted to prepare as many as I could to talk through. So this is what the tracks actually look like in a program called JMars, which you can download for free if you want to just look at planet data for fun. And each one of these blocks is one of those spectra. And I did a bit of work to essentially take these spectra and model the, abundance of the different minerals in there, and use that as an opportunity to map how the composition of dunes changes across Mars. But this is what we're talking about when we say imaging spectrometer. We mean it's a spectrometer in the sense that each pixel is I'm going to have to do this. Each pixel is a different spectra, okay? And so if we're looking at this, and I'm going to just stick to this one and zoom in a bit after I get through this, because that's helpful. But what we're looking at essentially from orbit, if we're doing remote sensing, whether it's imaging or spectra, no, I won't bother with that. Let's assume that you have a bad resolution, right? So you can imagine yourself on Google Images and you zoom in and there's
you know, a car on, you know, the highway, and you can't really tell what the car is because it's blurry. You don't have enough resolution, right? So if you could get more resolution, if you could split this up, right, you would start to see what we see, what I showed you earlier with the imaging spectrometer, each individual pixel. Yes? Now, to get more information, you have to make inferences about what's below that pixel size, or you have to get a higher resolution imager. Now, this is just the cornerstone of instrument development, right? You either have a better camera, a better instrument, or you have to take the data you have and make better inferences from it, right? Until essentially there's nothing left to resolve. So, and this is a core fundamental of planetary science, because you do one mission, right? You spend a decade and you spend $2 billion to get that one data set, and you're never going to get it again, right? So, you're not going to get better or more details. You have to be able to learn as much as you can from that one piece that you're able to work with. And results from imaging spectrometers and orbital imaging spectrometers are restricted by their resolution and their field of view because of this. So you can have either too much volume or not enough detail, too much detail and not enough volume, right? So you're trying to answer what is that pixel and how is that pixel different from others, and you can't do that if you don't have enough resolution. So what we do is we try to make inferences about properties that are below the resolution, and this is essentially remote sensing. And you know, remote just implies that you're doing it without direct contact. I consider all of this to just be remote speculation, essentially, right? So remote speculation can depend on the sample or the target that you're working with. It can depend on the environment that you're working in. It can depend on the instrument that you're working with, and it can depend on the wavelength of light that you're interacting with, right? And also the depth of where that light is penetrating or where it's coming from is roughly proportional to the wavelength. So you can also think of, let's say I'm looking at this rock and it's covered in dust. Actually, I won't explain this because I think I have it here. Yeah, this is my research. I'll go into this. Unless, you know, can I field some questions for a little bit? If you guys, I see Cribbles might have had a question. I can take a quick pause. I see Fango, Nevek, Gog, Hydra, Logic, Cribbles. If you guys have any questions, feel free. I might just end up ranting. But I don't know if I had this show properly. I did want to do more than just have it up on the screen, but I have no plans other than just have it up on the screen because it's cool. This is a feldspathic breccia from the moon. So I believe I have it here. Yeah, it's Bechar, Algeria. It's the find that was 2022. So 1,522 grams were found, and it's a feldspathic breccia. But that's a good example of just, you could buy a space rock if you want. You know what I mean? When you discuss the pixels and images, this is the same as spectra. So how would you know what material this is? Is spectroscopy different from imaging? Good question. Yeah, so basically, I'm going to use the hyperspectral example for this. Hyperspectral image cube. So hyperspectral imaging is when you have images or spectra across a very wide band pass. I don't know if this is easy to see from your size, but if your picture, a picture that you see on your screen of me, if that's 3 colors, RGB, hyperspectral is 3,000 or 3,000,000 colors, right? With each layer of a image cube being a different one of those bands. And I think this kind of demonstrates it kind of well in that you can have a spectrum from right here to here spread about through an image. So each pixel is its own spectra for that one place, right? And if you're doing hyperspectral, then each layer of that image cube will relate to a different part of the spectrum. So it depends upon the kind of detector that you're working with. If it's a push broom, you recognize that worm thing was iron. Oh, okay. So I'm curious about it, how you figure. Okay, good. Okay. So when you discuss optical energy, are you just talking about a small portion? Exactly. Yeah. So when we talk about just a camera, just a picture, you know, we're talking about this really small portion of the electromagnetic spectrum, right? We're talking about that tiny band. When we're looking at something like doing the laser of that rock, that's actually Raman Raman spectroscopy is I'm not gonna say it's annoying, but it's awesome. It's just really freaking complicated. In that, let me see if I can find the slides I had prepared for this because I thought this question would come up actually because this is something that I wondered about. There we go. Yeah. So if you look at the infrared, which is when you're looking at everything has emission, right? Everything that has heat and everything has heat has emission in the infrared. And the molecules are vibrating, right? So in the infrared it's active and Raman is active, right? But the whether the vibration is symmetrical or not for the molecule has an effect on how visible it is in the Raman. So covalent bonds are generally strong in the Raman, while the ionic bonds are generally strong in the IR. And one thing that you can think about is Raman will have an advantage over IR because you can measure the depolarization ratio, which I don't even want to try to explain that, which you can't do in IR. With Raman, you can enhance vibrations of certain molecular groups. So I don't want to like get into the nitty gritty of Raman because this is just a whole other kind of spectroscopy. But when we're talking about using a point spectra, that is a laser, so a single laser, a 532 nanometer laser, for example, which is 700 nanometer lasers. There you go, red, right? You're just pointing that and hitting a rock and measuring how the signal of that laser at that one specific wavelength is changing. It's a point spectrometer. If you have an array, right, then you could potentially measure across the whole of multiple bands, right, of a whole range. I should be over this. If you have a multi-band spectrometer, then you have a several individual window. I should really just have this up. This is going to make it a lot easier. I'm sorry about that. Multi-band. This is a good like. So a point spectra. You have a laser, right? You're shooting a laser at a rock, and this is a 700 nanometer laser, right? And we're measuring how that changes after it hits the rock, right? So that's active. Now, let's say we have a array, a detector, okay? And we're using a spectrometer in order to achieve this. Then we can get a spectra across a full, let's say it's from, 0.5 microns to 3 microns, right? My writing isn't going to be good, but bear with me. Now, if we have a multispectral, then instead of being a perfectly continuous line like you see above, I usually use software so that when I move this, that moves, so bear with me if I forget to move it. Instead, you have bands. You have a very specific window that you can observe. So there are a lot of lunar spectrometers, so spectrometers that orbit the moon, that can only see in these very particular bands. And the reason we do that is because it's easier, it's cheaper, and we only need to look in these specific parts of the spectrum, right? We only need to see these parts of the spectrum to know whether, oh, it's this mineral or that mineral or so on. And then we have hyperspectral. And hyperspectral is just the same thing as what we talked about above here, right? But it's a much, much wider range. So you could be going from the start of visible or even the UVis, so the ultraviolet, right? The ultraviolet before there, all the way up to long wave, so LWIR, so that's long wave. Oops, see? Long wave, yep, long wave infrared. Should have scrolled down. So long wave infrared all the way over here. And then you could have all the way UVis, like down here. So hyperspectral it's a much, much wider band pass is what we call it. There's a lot of really weird terms for this. But I think to try to answer it better, I'll say is a lot of it has to do, I'll even show you, So I'm even taking a graduate class right now just to like refresh myself, and I'm realizing how much of the math I do not remember or want to ever think about ever again. You know, optical spectroscopy in particular, which is the reflection stuff, gets really, really insanely complicated. This is vibrational spectroscopy. See, this is where I got some of those from. But, you know, if you just try to, oh, where are these? Are they up there? Hello? Oh, there we go. Yeah. So, like the fundamental equations, we use Maxwell's equations to start. So you start with Maxwell's and you go down and it gets really, really juicy. And then it gets really, really scary. And then even the professor starts making mistakes. And this is when you start getting into, you know, if you have like a pile of regolith, you know, you'll have a reflection off of a reflection and so on. The response to images, pretty much, yeah. I mean, I should have used this word. This is a good word, fingerprint. One thing that helped me a lot when I was learning is the word fingerprint. So every you know, mineral or every material has its own, you know, unique spectral fingerprint. I bet I could find. And depending upon the kind of spectroscopy you're doing, it's different. But a lot of the images you'll see of people trying to demonstrate this look like that, where you just have the lines. So, all right, let me go back to where we were so I can keep track a little bit. How are we good on time? Are we good on time?
I'm just letting you go. Probably let's say wrap it up in about 20 minutes. Is that possible? If
Yeah,
you want
that's
to keep
good.
going. There's no
No,
stream
that's
today, so
that's.
you can just keep going. It's great.
There's no stream today. I didn't know that. What a scam. Okay.
I mean,
Well, we can.
he's on vacation, so
Is he? Oh, I didn't even know. I've not been keeping track. All right. Well, let's. I could just walk you guys through real quick in like 15 minutes, potentially, if I'm quick about it. This is a really interesting problem
okay.
that some of you might find. So if we look at the surface of Bennu, which is this asteroid I've been talking about, from Earth, when we try to figure out what its thermal inertia is. So thermal inertia is the ability for a material to conduct and store heat. So you can imagine a large boulder, right? It'll take a while to get it to heat up, but once it's heated up, it'll hold that heat well. But sand, it'll heat up quickly because it's a bunch of small particles, but it'll lose that heat pretty quickly as well. And we can align the size of particles to a particular thermal inertia, and that allows us to essentially estimate the particle size of an asteroid. So what's the average size of the boulders on the surface? And if we did that for Bennu back in the day, it was estimated to be so much. The boulders were so much lower inertia, lower thermal inertia than they looked when we got there. It was this anomalous problem. It's like they're either extremely porous. Actually, I think I explained this. Yeah. So it's moderate thermal inertia is consistent with a surface covering of small particles, but instead it lacked these abundant fines, and instead it was dominated by these large boulders. And these boulders we classified by reflectance as having like they're either dark or bright. And remember, these are the exact same samples as the ones that you were seeing earlier in the talk that were literal pictures from, you know, our little spot in JSC. So what's really cool is that in the same way that I have a little piece of the moon here, you know, this is a picture of a piece of the asteroid that we brought another sample of that we can then use to kind of relate these. These are hypotheses are as old as before we got the samples. So these dark and these bright boulders actually seem to correlate with thermal inertia as well. So it seems like there's something going on. You know, the darker ones tend to have a lower thermal inertia, with the brighter ones tend to having a higher thermal inertia. And what's weird is that Bennu overall has fewer of these smaller particles, but a lower thermal inertia compared to other, you know, airless bodies. And so it's kind of suggesting that the large boulders on Bennu have really, really rough surfaces and low thermal inertias. Uh, and we believe, you know, this is kind of several studies, but Della Justina et al. I think said it well. It was that boulder diversities that we see, the heterogeneity, right? So the bright and the dark, is probably because we're seeing the result of Bennu being formed from an impact of a differentiated body, where you have surface material, you have subsurface material of different colors, right? So this is a rubble pile is quite literally just a reaccumulation of space crap, right? So we believe we're just seeing that difference in material in the surface now. And to determine what made these source materials distinct, we kind of had to figure out why the dark boulders were anomalous, right? And why they're dark, potentially. So why do they have this lower thermal inertia? Well, they could have a lower conductivity, right? So this is the equation for thermal inertia. They could have a higher porosity, meaning more air is in them, or they could have dust cover. So I mentioned earlier that the depth of penetration is on the order of the wavelength of light of the observation. Well, if it's covered in dust, then your observation isn't penetrating far enough to actually understand what the rock is. You're just looking at the dust. So it'll look like it has a lower thermal inertia. And so if you take the bulk thermal inertia and relate it to the average particle size, we are essentially reducing, the scope of our observation by making these inferences to get at these physical characteristics of the boulders. And, this is essentially the cornerstone of planetary science. I won't go into this too much because this is getting into the nitty gritty of like my dissertation and some of the definitions from that. But here, I'll get off this. Oh yeah, this is exactly that. So, the signal is coming from a depth roughly proportional to the wavelength of the light. And so you will need more information if there's a significant amount of dust cover that's preventing you from seeing that substrate. Go ahead, Gribbles. I'm going to see if we can find a slide that... Okay, this is a decent question. So thermal inertia, I explained to the rock and the sand. This is that. Right, so rocks and soils will heat up to a higher temperature fast, vegetation and water to a lower temperature, right? But, they'll be able to maintain a higher temperature by default. And then, we do the same for like bedrock and dust. And you can see that a mixture of the two results in something very different. So this is getting into some of the thermal modeling that we're doing. There's no way I'll go into this because... Yeah. So this is when I was saying that different types of spectroscopy have their own kind of quirks. This is getting into thermal infrared spectroscopy. We have these different features that we define: the Christiansen feature, the Rostron bands, and the transparency features. We use these as constraints for determining that fingerprint. So it's not as simple as, this material has this spectra all the time. It's this material at this particle size, at this temperature, at this pressure, with this percentage mixture, with this instrument, has this spectrum maybe, because it's dependent on the signal to noise, the resolution, and all these other stuff. So we have to really dig down to the fundamental processes, the molecular interactions that are causing these signals, define what those signals look like geometrically. Like, these are literally just called spectral shapes, right? And then use those as a proxy for extrapolating elsewhere to figure out, okay, what is this spectrum made of? And I'll skip past this a bit. It also happens that the two different types of boulders we found in Bennu had two very distinct types of spectra. So I think it's really cool when you take a picture from orbit and you look at the regolith, and part of it looks bright, part of it looks dark. It's like, oh, okay, there's two different types. Then you look at the spectra, and you average it out, and all of a sudden there's two very distinct groupings. Oh, these are the dark ones, these are the bright ones. That's awesome. Where are these groupings most different? Well, it's in this region right here. And so we can look at this specific part of the spectrum to determine a ton about the entire asteroid. And we do this for all the other planets, right? It's about looking at those minute differences. And, if you even plot those differences out across the surface, right, you can see in color how these different spectra relate to the different size boulders. And this is, essentially what makes, I think, spectroscopy so cool. This is actually the inside of Parsec, so that chamber that I told you about. This is getting into those simulations that I was running to see how dust affects it. Parsec was actually leaking, and it still is. I'm working on fixing it. You can see an actual break in that O-ring right there that was causing the leak. And that's put basically like a 2 to 3 year hold on my dissertation work. Uh, we talked about the electromagnetic spectrum and it requiring, it having band passes, so certain parts of the spectrum are more visible or not than others. This is a CSI window, a cesium iodide window. So you can't just put glass, right, in the window to be able to look into the chamber to look at your samples, because glass blocks out parts of the infrared spectrum that you're trying to study. So you have to use a material that's, right, essentially transparent in that part of the electromagnetic spectrum. And that window got hydrated and it failed to the point that it bent to like I told people it looked like a used condom because it was just bent inward and outward and propped in, and it kind of looked like this, and that's because there was this metal spacer that somebody put in there that caused there to be a gap. And when we this vacuum chamber, right, so this is not even a very significant vacuum that it's pulling. It's on the order of 10 to the minus 5, 10 to the minus 7 millibar. 1 bar is Earth atmosphere. And it has the force to bend this optical element like that over time, just because that cesium iodide is getting hydrated. But I think I'll skip through this because that's all related to my research and kind of the references there. But I can field questions now. We're getting pretty close. I'm getting kind of tired myself, man. It's been a long few days of work and play, but let me see if there's a... No. I think I've hit everything that I need to for now. But I do want to follow up. I want to see if, because I expected to have more time. I did have a lot of time, actually, as you can attest there,
Yeah,
to
you were
prepare
a
for
lot, which we
this.
appreciate. We
I
truly
had
appreciate.
I had so much time to prepare for it, but as the right professional does, procrastinated and smorgasborded it. But I hope that this has been somewhat helpful if you had misconceptions about what planetary science is, what NASA is, or just like seeing pretty pictures of, I just can't get over the fact that, these are some of the materials from the first 10 million years in the solar system. These are the rocks that the Earth was made of, right? These are the fundamental building blocks of not only the planet, but life itself, right? And one of the talks that we saw at the Lunar and Planetary Science Conference, that's LPSC this year, and this was really exciting because, we had the Bennu samples being opened for the first time and discussed for the first time. We had the first commercial lunar lander. I don't know if you guys know, but Intuitive Machines were the first company to successfully land a commercial spacecraft, which is really cool. Uh, and I think being able to go there and like meet the CEO, and talk to him about like the commercial sector and stuff got me really excited about the prospect for space exploration becoming a both palpable and accessible industry for all. So, whether it be, I have a telescope back here, right? Looking at Saturn or the moon from your backyard when the day is nice, or, buying a really basic telescope and jerry rigging it to be able to see, a piece of the moon. I think it's important to realize, or going online and just downloading the data, right? So if you look up the Planetary Data System, the PDS, you can actually access absolutely everything that NASA produces, all of the raw data from every mission, and you can do what you want with it. So showing people not only that this is possible for space exploration, but possible for all other kinds of industries is part of what I'm passionate about. And I think that they're part of the reason is because space exploration just seems like such a out of this world thing. You know what I mean? So please feel free to reach out if you guys have further interest in participating in an industry like this, or if you have questions about defense, about engineering, and you're new. I'm by no means an expert. I'm still technically a graduate candidate. I haven't even finished my doctorate, but I think I aligned myself early on to kind of get involved in a lot of the different industries, a lot of the different sectors of the industry early on, so I could choose exactly where I wanted to be. And I'd love to be able to, whether it be a warning or a blessing, right? Help you guys out. So again, I'll leave it out there for questions if any of you guys have them.
Thank you. Thanks for
Thank you.
doing this. We really appreciate it. Um,
Yeah,
Definitely, if you want to be back in 3 or 4 months, we'll definitely I'll talk to you about that. But
yeah,
definitely
for sure. I think once I get more of this room set up, we're gonna do things like attach stepper motors to the microscope and to the telescope, and so, we're gonna be streaming to all the different platforms so that this lab space can be essentially controlled by people around the
that's an
world.
insane
You
lab,
know,
by the way. And
Thank you.
yeah,
Yeah, no, this is part of my company and what we're trying to do. We're essentially trying to demonstrate, the accessibility of science, right? This is like eBay lab equipment that I bought for. So logic, everything that I have in here is less than 10 grand. The goal of my company is design basically a system for somebody to run a university level lab, like they are a professor, for a 10 grand initial seed, and then the operations that they would run in that lab would fund itself. So for less than 10 grand, for example, for planetary spectroscopy, you can get visible to near infrared spectroscopy, a Raman spectrometer, FTIR, a XRD, which was honestly a lot of it because it's an 1,100-pound instrument that we have to ship from Tennessee. An XRD is normally a $20,000 instrument, but we can buy it from somebody like a university who's getting rid of theirs because they have to spend money to hold it because it's a X-ray equipment. But we can, they offered it to us for basically free as long as we can get it out of their shop. So we have to pay to have it shipped, but then we have, basically a university class instrument for pennies on the dollar. And so, I want to build up the infrastructure for other people to be able to do something like this for, you know, whatever their industry is, right? I have a really, really significant fascination with, neural networks and ML and stuff, but I'm not an ML person, right? I don't do that kind of stuff. But I'm, our industry is very interested in whether neural networks can be used to better analyze spectroscopy data sets. Because as I said, squiggly lines, they're just gibberish without a lot of really complex math and physics. And it turns out that they're actually really stupid good at it. I have a colleague, Laura Breitenfeld, who wrote a paper that tried to estimate the abundances of the minerals in Bennu based on the same spectra that I showed you earlier. But she took a bunch of different mixtures of minerals, you know, every possible combination of these mineral mixtures that she could think of, put it in Parsec, that instrument I showed you, ran 100 something, 200 something different samples, fed that to a neural network so that it could estimate the abundances, and it was accurate to like less than 3%. Accurate. I mean, it was insanely, it was only off in like the olivine abundance by a little bit. So, and that it would take a researcher of my caliber, an extra 2 decades to get to the point where they could be that accurate by just glancing at one of these things. So the idea that we can use a ML model or even an LLM just to try to write science communications, for example, to try to simplify things for the broader public so that we don't have, flat earth conspiracies running amok and things like that in the world of this kinds of space research. So I'm really excited for the future of education as a whole. And, a low cost lab to be able to do stuff like this is now so much more accessible for even, you know, somebody like me, a graduate student. But this also allows me to connect with people like you and show you this, and it's a whole thing. I think it's important for us to now start taking our education into our own hands and finding access to these resources through open source means, because you're not going to get it in high school, and you're not going to get it in undergrad without spending an arm and a leg. Definitely. I'm excited to put it together. This is still like I'm like a week or two into owning all this stuff because it's been taking time to get delivered. For example, the FTIR, the person that shipped it didn't know how to ship an FTIR, so it came with the primary optical element completely shattered. Like there's little things like that are going to keep happening, but I saw it as an opportunity to learn how to be a PI, right? Learn how to be a lab manager for once and to test that out. So I think it'll be a good opportunity for me to prepare for when I'm a professor, but also it'll be a fun opportunity for like people on the internet, you know, to see what it's like to be in what a lot of people felt was such an exclusive industry, I guess I should say. But yeah,
All right.
thank you again for your time.
Okay.
And if you guys have any other last minute questions, you can email me. I'm tinker@thetinker.org, or you can Google me and find my information there, or any of the papers if you're curious about any of the stuff that was in that. Thank you very much for the questions, Kerbals. Really appreciate it, and look forward to learning more from you guys in the future.
Bye. Have a great night, everyone. See you guys later.
Have a great night.
Oh, and
Cheers.
no lecture next week, but the following week there should be one. So, see you
Sounds
guys
good.
later. Bye.